going to finally get to passive dynamic walker, and we are going to derive the equations. And then once we derive the equations, we'll use MATLAB to simulate, animate, and of course analyze the system for stability. Okay, so in this case, just like we talked about the bouncing ball, we had phases of we have phases of motion for the walker. So we have a phase where one leg is on the ground and the other leg swings, right? And this is what people call a single stance phase. There's a phase where the red leg, which is a swing leg, hits the ground. So in this case, the black or the stance leg is going to be the trailing leg, the one behind, and then the red one, which was swinging, is going to hit the ground, and that's what I would call the foot strike phase. And then you have again single stance. Okay, so let's try to identify this through the repeating unit which we talked about earlier. So we have single stance followed by foot strike. Then we have single stance foot strike. That keeps going on. So you can clearly see that the repeating unit is perhaps uh, either this one, use a different color for this, green. So starts here, ends there. Uh, that's going to be our repeating unit. And then we also have to put some conditionals over the arrows. So when does this go from single stance to foot strike? So when the foot detects the ground, so detect ground, right? So when the foot here, the dot I've drawn over here, is at the ground level, that's when you want to switch to foot strike. Okay, and then after this foot strike, there is a plastic collision right after foot strike, where the the dot on the red line or the swing leg sticks to the ground, so that's the plastic part, and then the black line actually starts moving, which is the swing leg. So let me draw that. So the red one is the stance leg, the black leg is the new swing leg, and that's going to swing. Okay, so we have identified the repeating unit, which means that we now need to write the equations for all these things. One is single stance, B is critic ground, C is the foot strike, and the plastic collision. Okay, so this is actually, there's no separate equation for, there's only one equation for this phase. Okay, the foot strike actually happens with plastic collision, so I shouldn't have written it quite this way. Here actually, my bad, this foot strike involves a plastic collision. And then the switch is really not conditional, it's just that it happens over an instant, and then things, the black leg leaves the ground. Okay, we don't have anything over here. Normally when you have a more complicated robot, you will actually use a condition that the reaction force on the trailing leg, which is the case, the black leg is equal to 0, and that's when the back leg, or the in this case the black leg, will lift up. Okay, but we won't have any condition over here. Okay, so we need to write equations for single stance, detect the ground, and foot strike, and that's what we're going to do. So equations for one single stance, two foot strike, and then 3 detect ground. The detect ground condition is actually pretty simple. If you have whenever the foot hits the ground, we will have essentially an isosceles triangle, and so there's a condition on the angles, and it's really pretty easy to get that. Okay, so this is not really a big deal. The one and two, however, are kind of tedious. We'll actually go through the derivation of those equations in a bit. So let's derive the equations for single stance and foot strike. One single stance. Okay, now before we derive the equations, I need to sort of make assumptions on the mass and inertia and so on. So here is how I will um, depict the walker. Okay, that's the leg on the ground. The red one is the swing leg. Okay, so this point, the point on the floor is always going to be called C1. The the foot of the swing leg is always we're going to call C2. We'll assume that there is a mass on the hinge joint. Okay, there's a hinge joint which connects two legs, and that's H. So this is sort of a, you can think of the body to be a point mass, and we don't put a body with inertia, but we just put a point mass on the hip just to represent the body. Yeah, then we'll assume that both legs have some mass, and this, let's just call those points G1 and G2. And then for the angles, the way we'll define this is uh, just to make it convenient, we'll actually define our frame to be along the ramp axis, okay, such that when we drop the perpendicular, we're dropping the perpendicular to the slope and not to the ground. Okay, the ground actually is at an angle of gamma. This is the ramp slope. So, but it makes it easier if you define it with respect to the slope. Now we'll call this angle the angle made by the vertical and the stance leg as theta 1. Okay, that's actually the absolute angle. Absolute angle is usually referred to an angle made with the external reference frame. In this case, it's going to be the ramp, and then we'll have another angle um, for the angle between the two legs. So in this case, what we're going to do is we're going to define it from here to here, and then this is actually uh, negative theta 2. And the reason why it's negative theta 2 is because when we normally, so this is slightly a weird way of looking at the figure. The really the way we would like to draw this, which makes it easier to think of the derivation, is we'll draw the stance leg, and then we'll draw the swing leg, but instead of putting it behind, we'll put it in front because our convention is actually positive, is counterclockwise, and you'll see that in a bit. So this is theta 1, and now you can see that the angle made with the stance leg with the swing leg is theta 2, so that is positive. And so when you take the swing leg and you move it backwards, like I've shown it in this figure, that theta 2 becomes negative, and that's why I put it the way it is. But this is easier to visualize and also to derive the equation, so I'll use this figure. Okay, so a few more things here. We'll assume that the mass of the leg is m, and do I have inertia? I probably do have inertia. Okay, we'll assume that they have a mass m and inertia I, and this one is a mass m, inertia I, and then we assume that the mass on the hinge has no inertia because it's a point mass. It only has a mass capital M, and then what I'm missing is the length. So assume that both these legs are of length L, and then we'll assume that the distance between the pin joint in the center of mass of the leg is C. And the same for the other one. Okay, so let me redraw that here. Let me just zoom this a little bit. Okay, so let's put G1 here, G2 here, H here. Okay, so I think we are ready to start the derivation. Now, the closest to the derivation of a passive walker is actually the double pendulum, which we have talked about in the previous class, where you assume that this point is pinned or hinged, and then you can derive the equations. Okay, so that's one way to it. You can assume that to be pinned and then derive the equations, and then you need to put the same thing. So when the legs switch, then you put the same thing here, and then you'll do the equations. So that takes more time. So I'm going to do a shortcut here, which will really help us to not only derive the single stance equations, but it will also make our life easy when we try to derive the equations for foot strike. I'm going to do is I'm going to assume that this point, that is the stance leg, has coordinates x comma y. Okay, and this way of deriving the equations where we have x, y, theta 1 and theta 2 is what is known as a floating base, because we not only have theta 1 and theta 2, which are the degrees of freedom of the legs, we also have x and y. Sometimes people will put the floating base here, that is, they would have x and y over here on the hip edge, which is another way of doing it. It turns out that if you put x comma y at the stance leg, then there are some simplifications which come with it, and that's what I'm trying to do it. In fact, you can try to derive the same equations and do the same simulations by assuming x comma y at the hip joint edge. Okay, so I will not do that, but it can be done. Okay, so that's the floating base. Okay, now next I'm going to use the Euler-Lagrange method to derive the equations. Okay, so remember the steps: find the positions, velocity. Second, find the Lagrangian. And the third step is derive the equations by using d dt is dl dq dot minus dl dq. Okay, and then if there are constraint forces, you need to put them here, external forces. Okay, so what we'll do is we'll go through these steps for the floating base, and then I'll show you how the equations turn out. Okay, so we go to step 1, okay, which is finding the positions. G1, C1, C2, G2, H, and then theta 1, theta 2, and then we said this is x comma y. Okay, so here pretty much what we need to do is we need to find the positions of pretty much all the points, because they will be needed some place or the other. So let's start with the position of R C1, which is this point, and that's easy. It's x and y because we chose that to be x and y. Next, let's find the position of RG1. Sorry, RG1 with respect to frame 0. Okay, I forgot to say the frame 0 is basically this frame which is fixed to the ground and is actually right here, x0, y0. Okay, so same convention we used previously. We put the base frame at the first point of interest. So now what I need to do is write this position vector, which is going to be, and I'm going to use the homogeneous transformation. So I'll need to do RG and 1, and then I would have R10, O1, 0, 0, 1. Okay, so that's basically this point, O1, 0. And then R1 basically describes the relation between this frame x1, y1 with respect to x0, y0, which I will write in a bit. And then we'll have the position of point G1 with respect to, sorry, it basically the position of G1 in frame 1, right? Which is basically the position of G1 in frame 1. So you can see that G1 has a y coordinate along y1. It doesn't have an x coordinate, it's basically 0. So the x position is 0. The y position is, hold on, I think I'm doing something wrong. Okay, so my bad. So the way I did this was, and this is actually a valid way. Turns out that the way I did this was, instead of assuming y to be along the leg, I actually assumed x1 to be along the leg, which doesn't really change anything. It just changes the way my rotation matrix would be. And this is the convention I used in deriving the equations. Okay, so I assumed x1 to be along the leg, and that's just because it makes my life easy. So if x1 is along the leg, then the location of g1 is going to be, so we know that this point is C from H, and then the distance from G1 from the base from C1 is going to be L minus C along the x-axis. It's going to be 0 along the y-axis. And then I need to put a 1 just to make the homogeneous transformation consistent. Okay, so given that, let's define what O10 is. O10 and is basically the position of O1 with respect to frame 0, and that's going to be x, y. R10 is basically the angle made by frame 0 with frame 1, and that's basically, so x1 is this way, x0 is this way. I need to find the angle between the two. You can see that that angle is, so if this is theta, then this has to be theta 1. And then since this is pi divided by 2, we can see that the angle between x0 and x1 is pi divided by 2 plus theta 1. So all I need to do is say, I'm going to say C1 S1, sorry, C1 minus S1, S1 C1, where C1 is cosine pi by 2 plus theta 1, and S1 is sine pi by 2 plus theta 1. Okay, so that takes care of finding RG1. Okay, I also need RH, which is the position of the hip, and that's actually it's a simple extension of what we have here. It's just going to, since it's sitting right on the x1, all I need to do is keep the homogeneous transformation as it is. I only need to change the position of h with respect in frame 1. So instead of having L minus C, I'll have L for the position along the x-axis or x1 axis, 0, 1. Okay, and then it's easy to find that because I already found out R10 and O10. Okay, so that takes care of RH. Okay, next let's go and find the position of G2. G2, I do the same thing, which is RG2 with respect to frame 1 is going to be a homogeneous transformation times the local distance of frame 2 with respect to frame 1. So the way I'll describe frame 2 is x1 will be along, x2 will be along C2, and then y2 is 90 degrees to C2. Okay, so with that, let me start writing this down. So first of all, I would have R21 021, 0, 1. And since the position of G2 along X2 in local frame, that is C, I can just put C for the X, 0 for the Y because the distance along Y is 0, and then 1. Okay, so I need to find O21 and R21. O21 is the coordinates of, I should put it down here. This point is O21. It's the position of O2, this point in frame 1. Okay. So frame 1 is this. So in frame 1, point O2 has a local coordinate of L because it's along the x1 axis. The y-axis is 0, and then there's 1. So just L and 0. So the x, this is along x1, along y1, it's 0. Okay, then we need to find R21. Okay, R21 is basically the angle made by frame 2 with frame 1. So let's just draw those frames. So x1, you can see over here, is upwards. x2, as you can see, is this way, in the blue. So let me draw blue. So I need to find the angle between the two. Okay, so let's see. So we have theta 2 is this angle, and then this angle has to be pi, right? If because that's a straight line. So the angle between the angle made by, hold on. So there's something not right. What I have in my notes is the angle is theta 2 minus pi. I'm just trying to see how that can be. This is also theta 2. Let's see how we derive the expression for the angle between x0 and x1. So we had the vectors like this, and then it's basically the angle between, you have to put both the vectors such that their tails are sticking at the same point and they diverge. And then here we should do the same thing. Either the tails or the heads should match. So it's the angle between, angle made by x1 with respect to, oh, I see. Okay, so I think it's this angle, because it's always the angle between the first vector and the second one. So that angle is, in fact, this is the angle of interest. So in the previous case, we went from x0 to x1. So in this case, we need to go from x1 to x2. And when you want to look at the directions, always has to be either the lines originate from their tail, so they're joined towards each other with their tails to touching against each other, the heads touching to each other. In this case, the heads are touching, which is fine. And so this angle is basically pi minus theta 2. Is that right? So pi is this. So here's where you have to be careful about the directions too. So this angle is pointing this way. So we have it this way. And so this angle, if you change the direction of the angle, you have it minus theta 2. Something is not right. Theta 2 minus pi. Okay, so okay, we can maybe look at it this way. Theta 2, this is theta 2. So this is pi. So that angle is pi minus theta 2. But okay, so the direction, my bad, the direction is actually this way. That's pi minus theta 2. And since I'm looking at the angle which goes from x1 to x2, I need to switch the sign. So if I want to go this way, it will be minus of pi minus theta 2, which is theta 2 minus pi. So R2 is going to be C2 minus S2, S2 C2, where C2 is cosine theta 2 minus pi, S2 is sine theta 2 minus pi. Okay, so that gives me RG2, and RC2 is just at the distance of L from H. So RC2 R10, sorry, R okay, nobody told me this. I think I'm doing a mistake here. This should be RG21. What I'm missing here is the other homogeneous transformation. It should be R2, R10, O1001, because it's always homogeneous transformation times the other homogeneous transformation, and then the vector C001. Okay, so the same thing should go here, which is if I want to find this, it's going to be H10, H21, and then the distance of C2 in frame 2 is L01. So I would have R10, O10, R21, O21, 01, and then L01. Anyway, so this is something which MATLAB will do for you. Something which I'll put in MATLAB. And then the only thing which is left is the fact that all our derivations, all our positions are in a frame which is along the ramp. So we need to convert from ramp frame to the ground frame. And so you can see that if this is the ramp frame, sorry, the ground frame, this is the ramp frame, the angle here is gamma. So gamma. And so our vectors are all in this frame. For example, RG10. If you want to find the vector in a frame which is along the ground like this, then we need to then transform those equations from ground frames to the frame which is along the ramp, ground. So there is a transformation R which will help you do that. So I'll write that down. But RG1G, G2 ground frame is the same transformation times G2 0, RH, G is R, G, RH 0, and so on. And this R is basically given by gamma. So that's actually turns out to be cosine minus gamma sine minus gamma sine minus, sorry, minus sine gamma cosine minus gamma. And the reason there's a minus gamma instead of gamma is because the angle from G1, so this angle, let's write this again. Okay, this angle is this way. This is the base frame. This is the ground frame. Sorry, this is other way around. This is O, this is G, the ramp. Since so this is gamma. Since we want to go from uh, O to G, we need to use the negative of this value, negative gamma. And that's why we have a negative sitting up here. Okay, so this is fairly tedious, but this is finally what you get for the positions of different points. Okay, so once you get R, G1, G1, G, it's going to have two coordinates, X, G1, G, Y, G1, G, and then R, G2, G is going to have an X, G2, G, Y, G2, G, and then R, H, G will have X, H, G, and Y, H, G. And we'll actually use the Y component a little bit later. Okay, so this gives us the positions. Now let's find the velocity. The velocity is, when we find the velocity, we'll just use the ramp frame to derive the velocity. So velocity in G1 is simply going to be the rate of change of position. So we already found RG1 with respect to frame 0. That was somewhere here. We found that. So we just take the derivative of that term. So that will be taking the derivative of G1 and Y dot G1 and so on. You could also use the Jacobian. So in this case, you'll use the Jacobian of G1, and then you will have Q dot. Q dot is going to be X dot, Y dot, theta 1 dot, theta 2 dot. Okay, and JG is going to be D so dxg1 0 with respect to dx, and then dyg1 with respect to, sorry, it should still be dx, should be with respect to d, it should be, well, so it should be 2 by 4. So clearly it should be yg10 dx, and then xg10 dy dx g10 d theta 1 dx g d theta 2 dy g1 dy dy g1 d theta 1 dy g1. So that's going to be the J matrix. And then if you multiply it with this 4 by 1 matrix, you'll end up with a 2 by 1, which is precisely what will be over here. So you can do it using Jacobian or using the derivative. And so you'll have to do the same thing for velocity of h and so on. Okay, so that's the hardest part. The easier part now follows. Okay, so we got the positions, we got the velocities. Let's go to the Euler-Lagrange, okay, which states that d dt dl dq dot minus dl dq equals the constraint force. Okay, now this is where things are going to be slightly different from what we have seen so far. In this case, the constraint forces are, well, there are clearly torques if you wanted to put them, but other than the torques, I think I skipped one step. This is basically after I get a Lagrangian. Let me just write the Lagrangian first. Move this down. Okay, this is step 3, sorry. Okay, step 2, I forgot. Lagrangian is T minus V. So the kinetic energy is half m Vg1 1 dot Vg1. So this is a way in which you can get the kinetic energy, or you can do Vg1 transpose Vg1 plus half mvg2 transpose vg2 plus half capital M vh transpose vh. The potential energy is, uh, oh, so I forgot the rotational energy, which is going to be half I omega 1, or in this case theta 1 dot square plus half I. So this is the velocity of the stance leg. The swing leg has an angular velocity of theta 1 plus theta 2. So theta 1 plus theta 2, uh, because the absolute angle made by the stance leg is theta 1 and the absolute angle made by the swing leg is theta 1 plus theta 2. So I need to do theta 1 dot plus theta 2 square. So this is the swing leg. And then finally, to subtract out potential energy, I would say mg. Now I would use y. So since capital M is associated with the hip mass, I have to put yhg plus mass gravity vg1 with respect to g, mg vg2 with respect to g. Okay, so now I have got the Lagrangian. Now I do the Euler-Lagrange equations, which I wrote down here. Now the constraint forces in this case uh, are actually not only due to the external torques, but also due to constraint forces. When I drew this figure, I assume that this is a freely floating object. I put x, y here, but in reality, there is actually a force at the swing leg, and there's a force on the stance leg. So I need to enforce those constraints right here in the Lagrangian. Otherwise, you'll see that the passive walker will be flying in there. So in this case, what I need to do is I need to introduce. So since these forces are producing a torque at the joints, all I need to do is put the right Jacobian. Okay, so in this case, Jacobian of C1. So let's call this PC1, PC2, because this is C1, this is C2, transpose PC1 plus, sorry, PC1 plus JC2 transpose PC2. And you can think of this as the same as what we derive for Jacobian for static forces. That is, what we effectively did was, by introducing this JC transpose PC1 over here, we put the right amount of torque at the joint such that those forces will constrain this points to behave in the right manner, in this case, x, y would be stationary, and this leg, in fact, we just put it here for the sake of it, but PC2 actually is 0 because the swing leg is not acted upon by a force. I just put this to make it very generic. Okay, so as I said, I just put this to make it generic. This is actually 0 because PC2 is 0. There's no force on the swing leg. However, there is a force on the stance leg, so I need to enforce that. So when I do this calculation for the Euler-Lagrange equations, I end up with equations which look like this: mz double dot equals, or m, let's use z, b, we just put, I think it should be a function of theta, c double dot p theta, theta dot, and then we would have, you know what, let me just write it this way: mq q double dot equals bq q dot plus j transpose c1 pc1. Okay, this is what you get, where q is x, y, theta 1, theta 2. Okay, so this expression actually looks something like this: m11, m12, m13, m14, x double dot, y double dot, theta 1 double dot, theta 2 double dot, and then m21, m22, m23, m24, m31, m32, m33, m34, 41, m42 equals b1, b2, b3, b4. And then for the Jacobian, you will have, since this is 2 comma 1, which is basically the forces in the x and y direction, this has to be 4 comma 2. Okay, so the Jacobian self is J1, J12, J13, J14. Is that right? So normally it has 4 rows. So my bad, it should be 2, 1, 3, 1, 4, 1, J12, J22, J23, J24. The way I've written this, it's less confusing if I just write it down here first. So JC1 by itself is 2 comma 4. So it's 2 comma 4, and when you take the transpose, you get 4 comma 2. So it should be written as J13, J14, J21, J22, J23, J24. Okay, so 2 comma 4, and you take the transpose of that. So I would have J11, J21. This indexes should be changed. J11, J12, J13, J14, J22, J23, J24, and then P C1 along the X, P C1 along the Y. Okay, so this is what the equations will look like in MATLAB when you derive it. Now, what you can observe here is, first of all, the forces on the stance leg are not zero, right? They will be finite forces. However, you can see that this point, C1, is at rest. It does not move. It's because it's a stance leg. So X double dot equals 0, Y double dot equals 0. In other words, if you look at the first 2 lines of this equation, it basically gives you the reaction forces. So 1 and 2. So 1 and 2 gives PC1X and PC1Y. Okay, it doesn't give you anything more than that. Lines 3 and 4 are the actual equations of motion, which help you to solve for theta 1 and theta 4. So if you want to rewrite, so I'll rewrite lines 3 and 4. So there will be M. Let me copy that so it's easy to see. Copy. Okay, so as I said, lines 1 and 2 gives you the reaction forces. If you want to see how it looks, let me just write it down first. Gives PC1X and PC1Y. So if you write it down, you get Since M11 is going to multiply with 0, this those drop out, we left with M13 theta 1 double dot plus M14 theta 2 double dot equals P M13 M23 theta 1 double dot plus M24 theta 2 double dot equals B1 B2 plus we'll have J11 and then J12 and it'll have J11P. So 4 by 2, 2 by 1, PC1X, P X plus J22 PC1Y. Something's not right. Okay, so this is basically going to give you, you can solve for these two. And then if you write 3 and 4, and since x double dot y double dot is 0, you have M33 theta 1 double dot plus M34 theta 2 double dot plus M43 theta 1 double dot plus M44 theta 2 double dot equals P3 P4 plus J13 PC1X plus J23 PC1Y plus J14 PC1X plus J24 PC1Y. Okay, so here the unknowns are theta 1 double dot, theta 2 double dot, and then PC1X, PC1Y. So there are 4 equations and 4 unknowns. So you can solve for those 4 unknowns using these 4 equations. JC1, right? So let me write that down. Jacobian is JC1. What's that Jacobian? It's basically the Jacobian of the position XG1, YG1, sorry, YC1, my bad, C1 and C1 with respect to X, Y, theta 1 and theta 2, right? And that's why it is 2 by 4. And then when you invert it, it's 4 by 2. The position of C1, which is basically this point, is simply X comma Y. And so if you take the Jacobian of this point, you'll see it something like this: dx, 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 dy, dx, d theta 1, dx, d theta 2, dy, sorry, dx. So okay, this is basically the x, which is common, the first part, and then dy, dx, dy, d theta 1, dy, d theta 2. So you see that it's basically, this is 0, this is 0, this is 0, that's 0, 0, 0. So it's basically 1, 0, 0, 0, 0, 1, 0, 0. And so essentially all these elements except for 1, 1, right? This is 0, this is 0. Sorry, J22 is not 0. All these are 0. And so is this. So the only non-zero elements are this one and this one. So it turns out it's actually much simpler than you think it is. It's basically, these equations boil down to first of all, this equation, which is totally independent of any reaction forces PC1, PC1x, PC1, because all these terms are 0. which is nice because now you can solve for theta 1 double dot and theta 2 double dot. And then you have these equations where you see that there's a PC1 and PC, well, this is 1 and this is 1. These two equations can be used to solve for PC1 and PC1x and PC1y, given that you know what theta 1 double dot and theta 2 double dot is. And these two theta 1 to theta 2 double dot comes from solving these two equations. Okay, to summarize, so let's call this 1, 2, 3, and 4. So I'm going to write the summary next. Use 3 and 4 to solve for theta 1 double dot and theta 2 double dot, which is basically this equation. Oh, it's 3, 3. 3, 4, M, 4, 3, M, 4, 4 equals P1, P2. So you solve that equation. It's very simple to solve. You just invert the M matrix and then use theta 1 double dot, theta 2 double dot. So solve for, and then once you solve for theta 1 to theta 2 double dot, use those to solve for PC1x, PC1y. Okay, so how do you do that? Well, it's M1, 1, theta 1 double dot, M1, 2, theta 2 double dot. Hope I'm getting it right. Oh, I think this is not right. There's no M11. It should be M13, M14, M23, M24 was P1, P2 plus PC1x plus PC1y. Okay, so this is used to solve these two equations. And so this is only if you need to find the reaction forces, because PC1x and PC1y are reaction forces. Okay, so that's just optional. I usually don't solve for these. I just use these two and I go from there. Okay, so that's basically equations of motion for single stance. Okay.